All right, so I'm partway through proving the main theorem, which is not this one. This is the lemma that I'm proving. There are two lemmas in the proof of the theorem. Remember, the main theorem that we're proving is that if you have a complete non-compact manifold with non-negative Ricci curvature, then the space of harmonic functions of polynomial growth is finite dimensional. Okay, and so this, the first lemma, which I mostly proved last time, is this is a kind of a decay estimate. So if you started, let me just remind you what's going on here. So we take any finite dimensional space of harmonic functions on our manifold, and so that's K, and then choose some basis, some orthonormal basis for K with respect to L2 on some ball of radius R about some point X. Then this lemma is saying that if I just shrink that ball a little bit by epsilon times R, so look on the ball of radius 1 minus epsilon times R about X, then the sum of the L2 norms of those basis functions add up to something which is independent of K. This is kind of the K estimate. In particular, if the dimension of K is very large, and this is saying that, you know, essentially all but some fixed number of them have to really decay very quickly. Okay, so last time what I proved was not quite that statement. So let me just remind you. Okay, so what I got up to, why isn't that working? There we are. Okay, there's something strange about this pen. Hopefully it will last through the seminar. Okay, so okay, we're assuming that R is 1. We can just rescale to make that the case. Then the observation was that if I take any point in this 1 minus epsilon ball, then I can bound the size of these functions at the point y by an integral, so it'll be some constant depending on n, and I got something like 1 plus rho of y divided by 1 minus rho of y to the power n times the average of u on the ball of radius 1, and here, sorry, u squared, and here I chose u to be a harmonic function such that u of y is equal to sum I equals 1 to k ui squared at y. Okay, so the point is, that's really the trick that made this all work, because I could do a little rotation just at that point y. I can rotate the space k so that only one of the basis elements, if you like, is non-zero at that point. Okay, so then because and this was given by a rotation in K, and what that means is that this integral on the ball of radius 1, this one here, I have integral on B1 of u squared is equal to 1, because they were chosen such that the integral of ui times uj is just a delta ij. That's the orthonormal basis assumption here. And so since I've just done a rotation, this is now just equal to 1, right? So this average over the ball of radius 1 is just equal to 1 over the volume of the unit ball. Okay, so on the left-hand side, this is just equal to u. Sorry, that's what I wanted. Now I can integrate over the ball of radius 1 minus epsilon, and I get, so this is the thing we want on the right-hand side, integral over b1 minus epsilon about x of this sum I equals 1 to k ui squared. And so that would be less than c of n over the size of the ball of radius 1 about x. And now I get the integral on b1 minus epsilon of this function 1 plus rho of y on 1 minus rho of y to the power n. Okay, so I should remind you that rho here is just the distance to the center point of the ball. So it's just distance to x. So in particular, rho on this ball is just between 0 and 1. In particular, on the 1 minus epsilon ball, this is no bigger than some constant times epsilon to the minus n on b1 minus epsilon. Okay, so that's not quite good enough to get the result that's claimed in the lemma, right? So they'll give me a c epsilon to the minus n minus 1. So I need to work a little bit harder to get a 1 extra power epsilon.
So Ben, just before that, Julie just made a comment about said there's something seems wrong with the scaling.
The scaling.
No, it's not very important. It's just the u of y because the sum of ui squared of y.
Yeah, sorry, that should be ui squared. Yeah, thank you. Yeah. In other words, the length. The length of u is the length of the vector u1 of y up to uk of y. Right? In other words, yeah, thanks. Okay, so to get a better estimate, I'm going to use a little integration by parts. Sorry, this is all, the idea is here to gain an extra power of epsilon. Really the observation, so the estimate here, the epsilon to the minus n, all I did was use the sup bound for this function on the ball, but really things should be a lot better because, let's see, if I think of this as something like this, this is the rho out here, then this function, well, it goes off to infinity at 1, and it's nice and bounded near 0, that's just 1 near 0, and so, and the height at 1 minus epsilon is epsilon to the minus n. So we're integrating a function that looks like that on the ball, and so most of the ball is actually quite small. So that's why we should be able to get a better power of epsilon. So to do that, let me, I'm going to use the Laplacian comparison theorem. Actually, so the key thing is to estimate, let's say on an annulus, let's say ball of radius 1 minus epsilon, but excluding the ball of radius 1/2, let's say. And let's see, it's enough. Really what I want to estimate is the 1 minus rho to the minus n. Okay, so the 1 plus rho on the top is just a bounded function, so I can just throw that away. Less than 2 or something like that. So that part doesn't matter. So I'm just going to look, just to avoid problems with the Laplacian comparison as you go to the origin. Okay, so I want to do an integration by parts, essentially. And to do that, I can just observe that I can just multiply by the gradient of rho squared, because that's equal to 1, right? At least almost everywhere. And now I can integrate by parts. So I just take one of those gradient rows and do an integration by parts. So let's see, in other words, I want to think of a gradient rho times 1 minus rho to the, minus n as the derivative of something. Let's see, how does that work? So the something then should be 1 minus rho to the minus n minus 1. And actually, I'm just going to make my life a little bit easier by subtracting a constant from that, epsilon to the minus n minus 1. So the constant there is chosen just to make it 0 on the outer boundary, on the b1 minus epsilon, on the boundary of the ball of radius 1 minus epsilon. Okay, so the gradient of that you can check is just equal to 1 minus rho to the minus n gradient rho. So I get, yeah, so it's that times gradient rho. And yeah, so then I can just integrate by parts. Since I've chosen it to be 0 on the outer boundary, I'll get a minus integral on the inner boundary. So that's just the ball of radius a half, the boundary of the ball of radius a half times this thing here, 1 minus rho to the minus n minus 1 minus epsilon to the minus n minus 1. And then I'll get the integral on the annulus of, okay, so I get this function, I guess there's a minus sign here. Minus epsilon to the minus n minus 1, and then I get Laplacian rho, right? And so now I can use the Laplacian comparison theorem. Laplacian rho is less than or equal to n minus 1 over rho. And here on outside the ball of radius a half, so this is, I guess it's less than or equal to, what is it, 2 times n minus 1. Doesn't matter too much what that is. The important thing here is that the integrand here is now of size no bigger than epsilon to the minus n minus 1. Okay, so it's clear that that computation, I haven't quite finished it really, but this is less than c epsilon to the minus n minus 1. Let's see, so there's, let me just make a quick remark here. This part here is also bounded by something like epsilon to the minus n minus 1. I have to take care of the size of the boundary of the ball, but that just comes from the volume comparison. The computation we did for Bishop-Gromov volume comparison says that this size of the boundary of the ball I can estimate in terms of, let's say, the boundary of the volume of the ball of radius a half. Yeah, so I end up with that estimate like that. And that proves our lemma, right? So we get on this smaller ball, the integral of the sum of the squares of the ui's is bounded by some constant depending only on n times an epsilon to the minus n minus 1. Okay, so that's the proof of that lemma. Really the thing that makes that is this nice little observation about doing the rotation in the space already in the space K. That's exactly the point where you show that the right-hand side is something that doesn't depend on K. So it's a nice idea. I think that's Peter Lee's idea. Okay, right. So now the other half of the proof of the theorem is kind of, well, designed to exploit that. See, so far the lemma 1 makes no mention of the polynomial growth, right? So it's just a statement about any space of harmonic functions. Lemma 2 is where I have to use somehow the fact that we're looking at harmonic functions of polynomial growth. Okay, so again, let K, now this time I'm taking K to be a finite dimensional subspace, but this time with the assumption of polynomial growth. So this is a subspace of HP of M. This was, remember, the smooth functions, so this would be U in C infinity of M, which are harmonic, so Laplace u equals 0, and with the polynomial growth bound, which says that the magnitude of u at some point y is bounded by, let's say, a constant times 1 plus distance y to x naught to the power p for all y. So x naught can be any fixed point. Okay, right, so essentially what we want to do is show that if you have this polynomial growth control, then you can find some ball which will more or less contradict what we had in lemma 1. Okay, so in other words, I want to show that in lemma 1 we had that the integral of the sums of the squares of the ui's is bounded by some constant times epsilon to the minus n minus 1. So the polynomial growth bound will allow us to say that I can get an inequality the other way, right? So the polynomial growth bound is really saying that as it goes to infinity, it cannot grow too quickly all the time. Right? And so essentially that's the idea here. If it can't grow too quickly all the time, then I should be able to find some ball on which the growth between the ball of radius sort of r times 1 minus epsilon and the ball of radius r is not too different. So it can't grow too much in that ball because of the polynomial growth. Okay, so the precise statement is for any point x in the manifold, and let's say any epsilon between, well, it should be strictly positive, so positive epsilon and let's say no bigger than a half. Any positive r naught and any positive delta, okay, there exists what you might call, a good annulus. In other words, an annulus where the size of these basis functions doesn't grow too much. Okay, so there exists an r bigger than r naught such that in the same situations, of course, I'm going to take ui to be an orthonormal basis, I equals 1 to k, is an orthonormal basis for k with respect to the L2 BR of x. Okay, so it's the same situation, same assumption that I had in lemma 1, right? So we had the ui's are exactly that, so they're orthonormal in L2 of the larger ball. Then, okay, the statement is, for this annulus, the integral on the smaller ball, so b 1 minus epsilon r about x, sum ui squared, must be greater than or equal to something which takes the form k times 1 minus epsilon to the 2p plus n plus delta. Okay, and keep in mind that the integral on the ball of radius r about x is of sum I equals 1 to n, 1 to k, sorry, ui squared is equal to k by definition. Right? So this you can really think of this as being this is just 1 minus epsilon to the 2p plus n plus delta times this integral on the ball of radius r. Sum ui squared. Okay, so in other words, it's really saying that on this annulus, these basis functions can't decay. They don't decay too much. Right? So it's kind of the opposite to what the previous lemma is telling us. Okay, so let's see how to prove that. It's essentially the idea is just what I described before. Because we know it's polynomial growth, we know that it can't be these harmonic functions can't be growing too rapidly all the time. Okay, and that's what we use to define some suitable R on which this can be done. Okay, any questions at that point? Okay, so proof. Okay, so we'll fix our x. Okay, so as in the lemma, right? We're fixing m, we're fixing epsilon, we're fixing an r0 positive and a delta greater than 0. Delta is just a fudge factor, right? So it's just, in a sense, yeah, it's just something that allows us to get a strict inequality, to get a contradiction. So it's okay. So then we're going to look at a whole sequence of radii, right? So we started with R0. We're actually going to look at all of the radii, let me call R alpha, which are...
Sorry, Ben, just to ask a question.
Yep.
So I must be missing it, but what depends on delta? Why can't we take delta to 0?
Well, just that the proof won't work if you have delta equals 0.
No, I mean, it's true for every delta, right? So
yes, but the choice, so for each positive delta, there exists such an R and so on.
Oh, okay. So
but I'm not claiming there exists one if you have delta equals 0. So it's not the same R for every delta, right?
Okay.
Yeah. So I'd like to be able to prove with delta equals 0, but the proof doesn't go through easy. But it actually doesn't matter for the proof of the main theorem. This is enough to get what we want.
Okay. Cool.
Yeah. Thanks. Okay. So the R alphas are given by expanding R0 successively by this sort of factor 1 over 1 minus epsilon. Okay. So then, yeah. So here alpha will be 1. Will be a natural number, right? So for each alpha, then I have kind of exactly an annulus between radius R alpha and R alpha minus 1 with this ratio 1 minus epsilon. Okay, and what we'll end up showing is that for at least some alpha, we will have the inequality that we need. Okay, so we'll argue by contradiction. So let's suppose that the claimed inequality does not hold. For all of these R alphas. For R equals R alpha for all natural numbers alpha. Okay, so really we'll get a contradiction to this. So the conclusion will be that there is some R alpha which this inequality holds. Okay, so somehow we have to relate what happens on each of these alphas to the one before. So to do that, let me, I'm going to define an inner product on each of the balls. Okay, so let G alpha, so remember K, our space of harmonic functions, is a fixed space of functions. And I can look at that space of functions as a Hilbert space with respect to L2 on whatever set I like, right? But in particular, if I look at L2 of these balls of radius R alpha, then I'll get inner products for each alpha, right? So let G alpha be the inner product on the ball of radius R alpha, on K, really. Coming from, so induced by L2 of the ball of radius R alpha about X. Okay, so in other words, if we have an orthonormal basis, let's say Ui, I equals 1 to K, is an orthonormal basis for K with respect to L2 be our alpha of x. So, okay, so that's kind of the assumption in the theorem. So that's looking at the case R equals R alpha. Then what we're really saying is that this inner product in this basis, G alpha ij, is just delta ij. Okay, that's orthonormal. And since we're assuming that the lemma does not hold, then we get that, okay, so if I look at G alpha minus 1 ij, that simply means the integral on ball of radius 1 minus epsilon r alpha of x ui squared, okay, because our alpha minus 1 is just 1 minus epsilon times r alpha. It's ui squared. Oh, sorry, I want the ij component, so this is just ui times uj. Okay, and so if I take the trace, okay, so in other words, the sum over I equals j, which just means, remember, G alpha is delta ij, so this is really taking the trace of G alpha inverse composed with G alpha minus 1. Okay, that is the integral on B 1 minus epsilon r alpha of sum I equals 1 to k ui squared. Okay, and that's the thing which we're assuming in the lemma does not satisfy this inequality. So in other words, that's less than k 1 minus epsilon to the 2p plus n plus delta. Okay, so it's exactly the assumption that the lemma does not hold for this r alpha. Okay, now what I want to do is relate different alphas. It's hard to do during the using the trace, but I can use the determinant. So let's just observe the determinant of G, what is it? So G alpha inverse composed with G alpha minus 1. Okay, this is less than or equal to. Now, so the G alpha and the G alpha minus 1s are both positively definite bilinear forms. They're inner products. So I can use the arithmetic geometric inequality. This is bounded by the 1 over k times the trace, G alpha inverse composed with G alpha minus 1 to the power k. Right? Okay, so plugging in what we know about the trace, that's less than the k's cancel, and I just get 1 minus epsilon to the, well, okay, so it's 2p plus n plus delta times k. Okay, and now I can chain these together, right? So I get, if I look at the determinant of, let's see, G alpha inverse composed with G0, okay? So I can write that as, just a product of the successive ones. So this is G alpha inverse composed with G alpha minus 1 times the determinant of G alpha minus 1 inverse composed with G alpha minus 2, etc., down to determinant of G1 inverse composed with G0. Okay, and I've got estimates on all of those. Each of them is less than 1 minus epsilon to the 2p plus n plus delta times k. Okay, and I have alpha of them, so I get this is less than 1 minus epsilon to the 2p plus n plus delta times k times alpha. Okay, right, so now, okay, now I want to just fix an orthonormal basis for G0. Okay, so this will be, again, I'll just call that ui, I equals 1 to k. Oops. So these are orthonormal in L2 of the ball of radius R0. Okay, this is the one we started with. Okay, so in other words, I get, yeah, so it just says that the integral on ball of radius R0 about x, ui, uj is delta ij. Okay, now I can observe that each of these is a polynomial growth harmonic function. So I get that ui of y is bounded by some constant times 1 plus distance from x to y to the power p. Okay, and there's only finite many of these functions, so I can take the c to be just some constant independent of I. Okay, so this is since the ui's are in, well, k, and that's contained in the HP, the harmonic functions of polynomial growth of order p. All right, so that tells me that, let's see, so, okay, so I'm going to use kind of the same inequality. So I'm going to write k times the determinant. This time I'm going to write g naught inverse composed with g alpha. Okay, and let's see, it's 1 over k. Okay, so arithmetic geometric inequality says that's bounded by the trace of g naught inverse composed with g alpha. Okay, and what does that mean? So g naught inverse is just delta ij, and the g alpha is the integral on the ball of radius r alpha. Okay, so this is just sum I equals 1 to k integral b r alpha of x ui squared. Okay, and now I can use the polynomial growth to say that's bounded by, so I get a constant r alpha to the p, at least if, let's say, if r naught is bigger than 1, or r alpha is bigger than 1, say, which it is for k large. Okay, so I have k of them, so I have a factor k, and each of them has, right, so the polynomial growth bound is, what am I missing? Oh yeah, I get the volume of the ball of radius r alpha. Is that all? Sorry, these are squared, so I get a 2p here. Okay. Okay, so I get, what do I get? CK. Okay. Okay, so I can bound the volume of the ball of radius r alpha by the volume of the ball of radius r naught times 1 minus epsilon to the minus alpha. That's just the Bishop-Gromov, sorry. Is that right? Yeah. Minus n alpha, sorry. So Bishop-Gromov says that the ratio of the volumes is no bigger than the ratio of radii to the power n. Right? So in this case, that would be minus alpha n. And then I get the r alpha is, so I get r naught to the 2p, 1 minus epsilon to the minus 2p. And that's it. On the left-hand side, okay, so I got the determinant of g naught inverse composed with g alpha. So that's just the reciprocal of the determinant I worked out before. Okay, so this determinant here, the inequality I've got on that now becomes a reversed inequality. So that's greater than 1 minus epsilon to the, okay, and I get the factor k, sorry. So I get 2p plus n plus delta k divided by k. I'm missing an, oh, it's an alpha, right? So it's this estimate here, right? And yeah, so it's just that one. I've taken the kth root, so the k is disappeared from the exponent, and that's the estimate I get. Okay, so what we end up with is this inequality here. And now I can cancel out the factors of k, and I can cancel out the 1 minus epsilon. Sorry, I took a reciprocal, didn't I? So there's a minus in front of all that. Yeah. So now I can cancel out the 1 minus epsilon to the minus 2p. I can cancel out the 2p alpha. Why is there no alpha there? Yeah, there's an alpha there, sorry. Because our alpha is 1 minus epsilon to the alpha. So there's an alpha in that exponent. Yeah, thanks. And yeah, so this exponents all cancel out except for the delta, right? So what we end up with is 1 minus epsilon to the minus alpha delta is less than or equal to, and the rest is just some constant, right? So the ball of radius R0 is just fixed, independent of alpha. The volume of the ball of radius R0 is fixed, okay? And so then our assumption really is that we have that inequality, 1 minus epsilon to the minus alpha delta is less than or equal to C for all alpha. Okay, and that's clearly impossible, right? So that's why I needed the delta, right? So I need the delta to make this left-hand side go to infinity as alpha goes to infinity. Right? So this goes to infinity as alpha goes to infinity. Okay, so that's not too bad. That proves the lemma, right? So so this is a contradiction. Yeah, okay. So the philosophy is just as I said, right? So you, if you had the reverse inequality all the time, then you would contradict the fact that it only has bounded rate of growth at infinity. Okay, so that's the two lemmas. Okay, so now I can prove the theorem. It's actually quite easy from where we are now. So the proof of the main theorem. And I think you can probably see where this goes. So we have one lemma which says that things have to decay if the dimension is too large, and the other one which says that at least on some suitable annulus they don't decay very much. We put those together, we get a contradiction to having a large dimension. Okay. So let's see, let's make that precise. So let K be any finite dimensional subspace of HP. So again, we're choosing epsilon between 0 and 1/2. So basically, I'm going to use the lemma 2, right? So I'm going to choose x0 R0, which we might as well take to be equal to 1, for example. Doesn't really matter. And delta also doesn't matter too much. So just choose some delta greater than 0, as in lemma 2, right? So lemma 2 provides us with some, it's all right. So lemma 2 gives us an R bigger than R0. Okay, such that this inequality holds. So the integral on the ball of radius R1 minus epsilon about x, sum I equals 1 to k ui squared is greater than or equal to k 1 minus epsilon to the 2p plus n plus delta. Okay, so this is, in other words, use lemma 2 to give you an annulus on which these basis functions don't decay too quickly. Okay, So this is true, remember, for any orthonormal basis UI of K with respect to L2 on the larger ball, BR of X. Okay, and so now we apply lemma 1. Lemma 1 says that, well, exactly the integral on the left-hand side. So integral on the ball of radius r times 1 minus epsilon about x of the sum of the squares of the UIs is less than or equal to constant depending on n times epsilon to the minus n minus 1. Okay, and so I just put those together, right? So that tells me, let's see, so it says K must be less than or equal to, so C of n, epsilon to the minus n minus 1, and then I get a 1 minus epsilon to the minus 2p plus n plus delta. Okay, so that's the bound on K, and all that's left. So I'd like the right-hand side to be bounded by some constant times epsilon to the minus n minus 1. Let's see, if it depends on my choice of epsilon now. So now I can choose epsilon. Yeah. So I'm going to choose, yeah. So if I choose CP is fixed, if I chose epsilon in the wrong way, so to be too small, then this last term on the right-hand side would be large, right? So what I have to do is choose epsilon in the right way, and basically it has to be of order 1 over p. So we take it to be, say, 1 over 2p. Doesn't matter too much on the constant there. Okay, so what does that give me? So K must be less than C of n. So that would give me 2 to the n minus 1, p to the n minus 1, and that would become a 1 minus 1 over 2p to the power minus 2p, and the n plus delta part I can just bound by, let's say, 2 to the n plus delta. Okay, so that's simply a constant, doesn't depend on p. So in other words, this is just a constant depending on n. And the important thing is that this term here is bounded, right? So it's less than, what is it, e, I guess. All right. No matter how large p is. Yeah, and that's the estimate. So I get all of those other bits I'll put into this C of n, some C tilde of n times p to the n minus 1. Okay. Yeah, so that's the theorem. Okay, how am I going? Right. So the two lemmas, let's see. The first lemma, well, so the basic things that I needed there were the mean value inequality for subharmonic functions, right? So that's was really the main tool in that. And I guess I used also the volume comparison result there to control the sizes of balls. Lemma 2 just used the polynomial growth and the volume growth, the Bishop-Gromov volume comparison theorem. So those are really the only ingredients you need in order to do this. Okay. So it's actually a very robust proof. Let me just make a couple of remarks before I finish. So this is really an observation which I think is due to Bill and Toby. They apply this also in the situation of minimal submanifolds. Right? So suppose M, let's say of fixed dimension n, is in some Euclidean space, some probably large dimension big N, and let's suppose this is a minimal submanifold. So in this situation, okay, think about minimal surfaces are generally not of positive curvature. You don't expect to get positive Ricci curvature on a minimal submanifold, and then, in fact, the inequality usually goes the other way. That the curvatures will be non-positive for a minimal submanifold in Euclidean space. But you can still prove something similar. Okay, I need one other assumption, which is that it should have what's called Euclidean volume growth. So that just says that the volume of, let's say, the ball of radius r intersect m. Okay, that would be the Euclidean ball of radius r intersect m should be bounded by some constant times r to the n. Right? So yeah, in other words, the little n is the dimension of the submanifold. So really, it's up to a constant of proportionality here. It should be the same volume growth as you get in Euclidean case. Then the claim is the space of harmonic functions of polynomial growth of order p is bounded by well, so a constant which depends only on little n and, well, let me call this number something, C0 times p to the n minus 1. Okay, so the idea here, you don't have you don't have non-negative Ricci curvature, but you do have the ingredients we need for the proof. And so let me just mention the idea. First of all, there's the old paper by Leon Simon and Jim Michael, which proves, well, it proves various things, Sobolev inequalities, but also they prove a mean value inequality for exactly this situation. So harmonic functions on minimal submanifold, or more generally varifolds actually, on minimal submanifolds. Exactly, well, almost to the form we need. So it says that U, so Laplacian equals 0, harmonic function says that U of x is bounded by some constant times the integral on, so here, normally in the minimal surface situation, what you look at is these extrinsic balls. So ball of radius r intersect m. Okay, so I guess the one I want is integral of u squared is bounded by the more or less an average of the integral of u squared on the ball of radius r, with the, sorry, it's not r squared, the slight difference that instead of the volume here, we get the radius to the power n. Okay, so that's the mean value inequality. And then we also have, well, by similar ideas, actually, by the Monothnicity formula for minimal surfaces. This just says that d by the r of the volume, so of ball of radius r intersect m, volume meaning the little n dimensional volume, divided by r to the n, is greater than or equal to 0. Okay, and okay, so if we add that to the Euclidean volume growth, so the Euclidean volume growth says that this thing in the bracket here, this ball of radius r divided by r to the n, is increasing and bounded as r goes to infinity. And as long as we start at a point on the on the manifold, then it starts out being greater than or equal to 1. So, or greater than or equal to the constant, an n-dimensional constant. So it says the volume of BR intersect M is comparable to R to the N. Okay, so that does several nice things. It turns this one into an average on the ball instead of dividing by R to the N, because R to the N is now comparable to the volume of that ball. And it also gives me a volume growth condition. Okay, this says that the volume of B, let's say big R intersect M, about 1 center, divided by the volume of B little r intersect M. So I need to combine this monothnicity with this this comparability here. This is bounded by at least some constant times big R over little r to the power n. Okay, so that gives me really both of the ingredients that I need. I can just do the proof as before to get the finite dimensionality. Okay, so that's a nice sort of illustration of how robust the theorem is. This actually has a very nice implication, which perhaps I'll just finish up with. Corollary. Under the situation, so if you have a minimal submanifold with Euclidean volume growth, then M actually must be contained in a subspace of Rn of dimension depending only on little n and C0. Right? C0 is this Euclidean growth rate parameter. Right? So you have a bound on this, essentially the ratio of the volume of ball radius r to r to the n, C0. Then, in fact, the submanifold must be contained in a subspace with dimension no bigger than that. How does that work? So, proof, the coordinate functions on M are harmonic. Okay, so that's one way to characterize minimal surfaces, is that the coordinate functions are harmonic functions. They are of, well, they're also of bounded rate of growth, right? So the size of a coordinate function at radius r is no bigger than the radius. So it's so of linear growth rate. Okay, so I mean it says that the xi's, each component, is something in this space of harmonic functions of linear growth. Okay, and then so just apply the dimension bound. Okay, so it says if the coordinate functions now lie in a finite dimensional space of possible functions, that says that the image space is actually finite dimensional. It's a very nice little application of that result. I thought it nice to finish up with that because recently there's a nice generalization of that to mean curvature flow, also by Bill and Toby, using these kinds of ideas, but for the heat equation situation, which I think will be, well, at least the heat equation analog of these results, I think Glenn and Julie will be talking about in the next couple of weeks.
Yeah.
That's it. I'll stop there.
Thank you, Ben.
Thanks, Ben. Yeah.
Do you have any time for questions?
Well, I mean, we can stay as long. Anyone can stay as long as they like.
Yeah, but I mean, what about if Ben leaves? Then
oh, I'm okay. Yeah, I'm not in a hurry.
I think I'll I'll talk next week. I'm not going to start in 30 seconds now.
No. That's why I filled in that space of time. So
yeah, thank you. I've got a couple questions. So I don't know about the work on this for mean curvature flow, so maybe it's. But is there any kind of, so if you're talking about the submanifold situation, is there any notion of stability for these results under perturbations of the submanifold?
Well, yeah. I mean, so it is quite robust, right? In particular, let's see. If you look at the context of manifolds rather than submanifolds, that one's a bit easier to talk about. So remember, the ingredients you need are a kind of a volume comparison theorem, or a volume comparison theorem, and you need a mean value inequality. And both of those are actually coarse isometry invariants, right? So if you have an almost isometry, then all the results will go through. So in particular, you have a Riemannian manifold which needn't have non-negative Ricci curvature. All it has to be is coarse isometric to a manifold of Ricci curvature, which is really no control on the curvature at all. Right? It's just a coarse control on the geometry. Then you still get these results on finite dimensionality of spaces of harmonic functions. So it's really remarkably robust in that sense. And I guess, I mean, the same thing is true in the submanifold setting, although, I guess it depends a bit on what you mean by perturbations. You're thinking of perturbations in terms of functionals, perhaps, rather than...
if it's the intrinsic one, I was thinking in perturbations of the metric, but if it's the...
so perturbations metric behave very nicely, right?
Yeah. So what about if you have a submanifold and you apply like a Möbius transformation to it, like an inversion? Will this still... Will these results hold on the inverted submanifold?
Not uniformly. I mean, so, if you're doing an inversion, you might send a point to infinity and then your volume growth thing is totally destroyed, right? But,
sure. Yeah, that can happen, yeah.
But, so I guess you have to take care of some things. But
the case I've got in mind is when you have a minimal submanifold and you apply sort of formal transformations to turn it into a Willmore submanifold.
A Willmore thing, yeah.
And I don't know, I was just thinking the monothnicity formula is quite nice for Willmore submanifolds, and mean value inequality I don't know about. I don't know if that's going to work, but maybe a different proof of that could let it work. But then I was thinking, well, maybe there's just a direct way to see that actually it's still true on a Willmore submanifold.
No, I think there's no easy way to say it would be true globally, but of course, if you're doing locally a nice, it doesn't make sense to talk about the dimension result locally, but
yeah, sure.
I mean, you have problems where you're really blowing things off to infinity and so on. I think it's not going to be easy to handle those, I guess.
Well, I mean, if you're inverting a regular point, then infinity should not be so bad, right?
Yeah. So then if you had some assumption on what your original thing was like in infinity, then that should translate into nice properties on your inverted thing, I guess. I'm not sure.
Okay. Bye, Julie.
How about less regular situations? I mean, you have some notion, I guess, of harmonic functions in like a RCD space, maybe, of some Ricci limits, or maybe somewhere with just I don't know, like a smooth manifold, but maybe the metric is only measurable.
Well, I mean, anyway, we can see. Really, I mean, I'm using very little of any manifold structure in the proofs here, right?
Right, exactly.
All you need is this sort of some sort of volume doubling, weak volume doubling thing, and and a mean value inequality. And mean value inequalities you can prove if you know any kind of Sobolev inequality or isoparametric inequality.
Right. Right. So yeah, if we have something like these doubling spaces with the Poincare inequality.
Yeah, exactly. Yeah.
Yeah, that's what I was saying. There's nothing, everything's sort of integrals and volume. It looks pretty good. I mean, yeah, okay.
Oh, some of the tricks I did today, like the integration by parts, probably don't work. But actually, that's just a shortcut. All you really need there is the volume doubling.
Okay. Yeah, I mean, maybe some of these things, though, you can use like a weak upper gradient or something. I don't know. Yeah. There's some kind of like a Cheeger representative Lipschitz.
Yeah. I mean, that estimate of converting from epsilon to the minus n to epsilon to the minus n minus 1, you can do that just by splitting it up into suitable annuli, so a sequence of annuli with smaller and smaller radii, and estimating on each of those, and then it just uses the volume bound and not any integration by parts or anything.
Right. Okay. But so if you have, so a lot of this looks pretty. A lot of these things should be stable under like Gromov-Hausdorff kind of.
Yeah, these are definitely. Yeah, exactly. That's right. Yeah.
So you could sort of, at least for sort of a Ricci limit, you could just prove it in the smooth case and pass to a limit more or less.
If you know something is a limit of smooth things, then it should all work.
Yeah. Oh, that's very nice. Yeah.